Now this is from topic 3 practice set 2. Now this is a really difficult question, so do hear me out, and if there's a point in time that if you are not sure, please feel free to leave your questions in the comments below and I'll answer them. Alright, so water is flowing into an inverted upright cone with a fixed height h, okay, and fixed radius r. So what I want to emphasize is that when you look at the figure here, right, h and r, they are actually fixed constants, so do not use them to do not treat them as variables when you do differentiation. So just imagine that if you find it's very hard to swallow, imagine that they're just a number. All right, they're just a fixed number. They are not variables, so you do not differentiate them. All right, so fixed height h and fixed radius r, so it means that these two are actually constants. Right, so if I were to draw out the height h would be over here, and the radius r will be over here. Okay, so I'm not sure if it's shown in your notes, but this is how I will put it across to you. Right, so that the radius of the surface of the water is increasing, okay, at a rate of kcm per second. So here, right, let me just take this radius of the surface of the water. Now since this is the capital R, right, I'm going to use this as small letter r. Alright, I'm just going to call this small r over here. Okay, and similarly, the height of the water surface, I'm going to call it small h. So what you do see here is you see small r, small h, these two are variables, because as you're filling them up, this r will be increasing, this h will be increasing. So these two r and h, small r and small h, they are your variables. Whereas note that capital R and capital H are fixed constants. All right, they are fixed constants. They are actually the dimensions of the big cone, and they do not change. All right, so the next part, I want to say that, okay, so here remember that in connector rate of change, one of the derivatives will be given, one will be hiding, and one will be the one that gets you the marks. So the radius of the surface of the water, basically here, it refers to dr dt. So what are they trying to tell you is that dr dt is equals to k cm per second. Now this radius here is increasing at k cm per second. Now the rate of find in terms of capital H or R, the rate of change of the curved surface area of the cone that's in contact with the water when the cone is filled to 1/8 of its capacity. So of course this question is going to be a bit hard to swallow. So there is a need to come up with a few variables on your own. Now the first one, of course, is the curved surface area. Now how do we find the rate of change of the curved surface area? Now one of the things is that definitely we need to have another variable that represents the curved surface area. I'm going to call it S. Alright, I'm going to call it S. So the curved surface area here, let me just use the variable maybe S to represent it. S for surface, so it's easy to represent. And you can see that what are they asking for is they are actually asking for ds dt. They are asking for ds dt. Alright, so I want to find the rate of change of the curved surface area of this cone. Alright, so what we need to do is we need to find ds dt. The first thing we need to do is okay, we know ds dt is one that we need. This get us the marks. The one that's given is dr dt. And forming the rate of change equation, you can sort of see that the last one you need is probably ds over dr. Alright, so this is the one that's hiding. Okay, so it will tell you that you need the surface area as a function. This will tell you, a hint to you, that you need the surface area as a function of r so that you can do ds dr, which is what we are going to go ahead to do now. So how do we find our surface area? Now surface area here for the cone, remember, is basically just pi RL, right? So remember, if we go to back to JH1 2 knowledge, we know that the surface area of the cone is pi RL, where L is actually the slant height, okay, of the cone. Now in this case, right, if you consider that by Pythagoras theorem, I can also say that this L is none other than the square root of R square plus H square. Okay, is that okay with you? Alright, so because by Pythagoras theorem, R square plus H square is equals to L square. So L, this L here is R square plus H square, square root. That is my L here. And this is actually your curved surface area. Now here, my S is equals to the curved surface area is pi R square root R square plus H square. Take note, this is our L, which I have re-expressed this using a Pythagoras theorem. Okay. Now the next thing is, have we found everything in terms of R yet? We have not. There is still a H existing that we need to convert away into terms of R, so that we can do ds dr. Now I look at this H square. Now remember from all your notes, right? And if you look at this triangle here, one thing that will strike out to you is it is very prominent that there is a chance for you to use similar triangles. Okay, so if we use similar triangles, then observing over here, small r over big R would be the same as small h over big H. Alright, so using similar triangles, we can conclude small r over capital R is the same as small h over capital H. Now if you simplify this, you can see that your small h can be written of capital R HR, small r over capital R. Although this looks very confusing, do note that only R here is the variable. Okay, only R here is the variable. Capital H and capital R are constants. Okay. Now I'm going to take this and of course you can see the next part. What I'm going to do is I'm going to substitute this inside here. And you can see that your new refurbished and renovated surface area now can be pi R multiplied by R square plus HR over capital R square. Okay, don't note that capital H, capital R, they are not variables, they are constants. You do not have to worry about them when you do differentiation. They behave like constants, right? Because they are fixed as stated in the question. Now if I were to differentiate this, all right, so the next part is I can actually maybe just simplify this further so that it doesn't look so challenging when we differentiate it, right? So this is pi R square bracket 1 plus H square over R square. So what I did is I took out the R square and I put it outside, I factorize it, and this R square again can be brought out further out of the square root sign. This is like pi R multiplied by square root R square multiplied by square root 1 plus H square over R square. The square root R square is just R, so R and R, that gives me pi R square multiplied by 1 plus H square over R square. Okay, so now if you notice that since my R square here, this is the only variable, I think note that everybody else are constants, so you don't have to worry. Alright, don't have to worry. I can go ahead to do my dsdr. Alright, so here, if this is my S, I want to share with you is that dsdr, meaning when we differentiate S with respect to R, I'm only considering this as my variable. Everybody else are scalars. Everybody else, they are scalars. So this R square here, when differentiated, gives me 2R. Pi and the radical term here just remains as a scalar constant, and they are not touched at all. They are not touched at all. Alright, so there you go. This is your DSTR. Alright, so you can see that back into the game plan, we have sort of find our DSTR. Now what remains is the value for me to substitute in. Now the numerical value here, or that time which they tell me, is that in contact with the water is when the cone is filled to 1/8 of its capacity. Alright, 1/8 of its capacity. It means that, let's say if I were to consider probably this as the smaller volume, and perhaps let me use yellow, right? And maybe this as the bigger volume. Alright, now when they said that now the cone is filled to 1/8 of its capacity, it means that your V1, right? Your V1 is actually 1/8 of V2, right? Because they said it's 1/8 of the capacity. This tells you that V1 over V2 will be 1/8. Now remember, in JH1, JH2, when we look at similar figures, right? The volume ratio is the cube of the side ratio. It will tell you that this means that this is the same as your small r over big R cube. Alright, so the volume ratio is the cube of the side ratio. Remember similar figures, right? The volume ratio is the cube of the side ratio. So if V1 over V2 is 1/8, it will tell you that small r over big R cube is also 1/8, meaning small r over big R is 1/2. And remember that here, this R is the variable, the capital R is a constant. Alright, you treat it as a constant. So small r here is basically R/2. So this is the particular value you're going to sub. Remember, capital R is a fixed value that you can use. Okay, so what we're going to do now is that I'm going to form this equation already. Yeah? I'm already ready to use this equation. Alright, I'm going to bring it down, and you can see that this ds dt, alright, with this equation, my rate of change of the surface area of the cone, the r dt is just equals to k multiplied by this entire ds dr over here. Right, so if I bring this here, remember that the r here is actually at the instant, right? We can substitute the r as capital R/2. Capital R/2. Okay, so simplifying this, cancel. Then your ds dt is just k multiplied by pi multiplied by r. You can write it as maybe k pi r or pi r k square root 1 plus capital H square over r square. Okay, and with that, this is actually you can simplify to your final answer lah, which is k pi square root r square plus h square, simply by bringing the r into the radical sign. Okay, so this is a very difficult question. If there's any point in time you are not sure, do feel free to drop a message or comment below and I'll answer you. Thank you.